Okay, so we're going to do some examples calculating the rotational inertia, moment of inertia, of an object around any axis. The general description of the method was done in the last video. Remember that the total resistance to changes in rotations is the sum of the resistance to changing rotation of all parts. And the resistance to change rotation of any small chunk, right? So every chunk has a resistance di, that is r squared dm. How do we do this? We go 1, 2, 3, 4. It tells you what to do right there. So we sketch the object, we choose the axis of rotation. I'll do that over here. Then we go to dm. What's dm? Show it. Just show a little chunk, okay? And then we go to 2, and we go, we need r. Where's the r of the chunk? Well, it's from the axis of rotation to the dm. It's the shortest distance. 3, I need the limits of integration. So the coordinate range for all parts of the object. So you want to cover every single little chunk of the object that makes up the object. 4, we want dm in terms of density. Okay? dm in terms of density. dm of a chunk can be, in general, rho dv. Mass per volume times volume is mass. Right? But I'm going to write it for a particular chunk. If it's uniform density, then the density is the total mass over the total volume. But only if that's true. It's often the case, but not always. And then times dV of that chunk. Okay? So also true for mass per area times the area of a chunk. If uniform mass total over area total, dA again of that chunk. Mass per length of the chunk, length of the chunk. If uniform density, total mass over total length is the density. Everything has the same density, but that's not always the case. What if it doesn't? Then by engineering and by design and by a homework problem that's given just as an exercise, you could be given an equation for rho, sigma, or lambda so that each piece has a little different density. It can vary by some equation, just make a simple math equation and do it. Maybe there's an engineering reason why you design it that way so that the density varies with position. Okay? And then you just leave it like that, put in that equation, and go about your business either way. All right, fine. When we do this, the next step that I didn't put on the last one is to look at the dV of the chunk. Look at the dA of the chunk, or look at the dL of the chunk in terms of your coordinates. Okay? So write that down as a 5-step program here. Now we're going to need, I'm going to put it over here, it could be here or here. I guess I'll circle it right in here. Number 5. In terms of your coordinate system. Okay, let's see what I mean by that. So let's do it. Before I do that, I want to introduce you to the parallel axis theorem. It's a pretty easy derivation, but let's just write it here and you can look that up. The rotational inertia of any object depends on its axis of rotation, as we said. Now I could have 2 axes of rotation. I could have this axis of rotation or this axis of rotation. This one goes through the center of mass because I can balance it right there. That's pretty good. That's pretty much through the center of mass. If I know the rotational inertia through an axis that goes through the center of mass, like that, or like that, actually, any way that goes through the center of mass, then I can find easily the rotational inertia through any axis that's parallel. I can find it here, here, here. I can find it here. I could find it anywhere. In fact, I could even go way out here through this equation. So if I know this, I can find any of these. How do I do it? Well, I know that. I add on the total mass times the distance squared from the center of mass here to the new axis of rotation. So here's my starting point. Hopefully you can see that. And then d is the distance between those axes, and again, I can keep on going, and that still works. Pretty cool and pretty simple calculation. Right? There's also a perpendicular axis theorem, which you can look up and explore, and that's nice too. Kind of a nice little simple calculus problem. So let's look at some examples, and here's one. A rod with uniform cross-sectional area. That's kind of all I need here. So the rod could have a rectangular cross-sectional area, the end of a meter stick. The rod can have a circular cross-sectional area. Sometimes you'll worry about that, then the math gets a little messier, but the physics is still the same. So here's my rod, either one of these, with a uniform cross-sectional area. He's got a uniform cross-sectional area. Okay, good. Some things, could taper or whatever. Okay, so now I need to do this little game. I want to calculate the rotational inertia of the rod. But you really can't, because not now, I don't know what axis. It depends on which axis you rotate around, right? So feel it. This is harder to speed up, slow down, speed up, slow down, speed up, slow down than this is, and yet it's the same object. This is getting harder, getting harder, getting harder, getting harder, okay? So the rotational inertia is not a property of the object, it depends on which axis of rotation. As just a little aside, in upper division, engineering and physics, you might try to encode all the possible axes of rotation that this object could have. It's easy to spin it around there. Okay, and so that would be like this. I'm going to erase this in a moment. I have an object would be written. Don't worry about this. I just have to show it to you. Z, I, X, Y, I, X, Z, I, Y, X, I, Y, Z, I, Z, X, I, Z, Y. It's a 3x3 matrix called a tensor. And then you could say, okay, I'll throw that thing in the air, make it rotate however, and in general, that characterizes the whole thing. But until you get there, which you may never, many folks don't ever need that kind of thing, but it depends on your applications, what you're doing. You need to choose an axis of rotation. So let's choose an axis of rotation. Let's do this thing. Let's choose it, I don't know, through the center of mass. So here's my center of mass, which is the average position, uniform density, or whatever the case is. So I'm going to assume that it's a uniform density. Put the center of mass there. So I'm going to say, okay, here's my cases. Uniform density. Now, which density am I going to talk about? Well, the area for any chunk is going to be the same. The cross-sectional area, the end. So I'm probably going to be talking about the mass per length. Okay? And since it's, in general, I'm going to say mass per length of a little chunk. And since it's uniform, I can make that mass total over the length total. But I'm deviating, right? That's fine. I'm just writing down ideas as they come. Here's my axis of rotation. It doesn't have to be rotating. It's still got inertia, whether or not it's rotated or not. So here it is. There's my axis. And I'm going to call that axis A. And now I'm going to go through my steps. Oh, let's see, what did it tell me to do? Sketch the object and the axis. I did that. dm. Okay, what do I want? Let me just keep in track of what I want. I want the I total around axis A. Well, what is that? That's the integral of I of each chunk. This just helps me take little baby steps, and baby steps really do help. So now I need the I of each chunk. Let's see, I need to show dm. This is r squared of the chunk and dm of the chunk. That's what the rotational inertia is of that chunk. So let me show the chunk. What color should the chunk be? Let's make that chunk. I don't want to do it at the center, not at the end, not halfway in. Let's just do it somewhere. There's my chunk. Small chunk. Okay. Chunk. Okay, so we've done that. Step one. Step two, where's R of the chunk? Well, R is from the axis to that thing. So, fine. Let me see. That would be R here. So show it. That's R. Now, you might want to put this in a coordinate system. So this looks kind of standard. I might just do this. X, Y. Okay, fine. So now, R, in terms of that coordinate system, would be X. R would be fine. I don't want to put it in terms of X. Okay, great. So I got that guy. Let's see, that's the integral of X squared of that chunk. Okay, cool. Got that handled. What was the next step? Well, look at it. I showed that. I'm going 1, 2, 3, back to 4, and then 5. I need, what do I need? I need dm, let's see, got the dm, I got that, what do I need, what do I need? You got it? Okay. Limits of integration, where are all the chunks? They go from what to what? Well, in this picture, I could set my coordinates any other way, just look at your picture, because that's the key, is that I'm going to go from, well, negative L over 2, where L is the length of the rod, to positive L over 2. So that's my integral, negative L over 2 to positive L over 2. All right, cool. Got that part. Now I need dm. So let me just do that over here. dm is equal to, well, it'd be lambda dl of the chunk. Lambda, what's that? Lambda, this is a constant. If it's an equation, then I'll put in some equation, maybe as a function of x that I'm given. But here it's not. I'm told that it's a uniform density, so then that's the total mass over the total length. Fine. And then what's dl? That's step 5. I need to put dl in terms of my coordinates. Where's the length of the chunk? How long is it? Is it this long? Now the length of the chunk, that's where dl is. And dl in my coordinates is the same as a dx. So now I'm just making it specific. dx of that little piece. All right, cool. So now I've done some good work here. I've turned this guy into mass total, length total, dx over all the possible pieces, this piece, this piece, this piece, and then I will get the total rotational inertia. Now it's math. You've done the physics. So setting this up, if you can do that for any equation, different physics, draw your picture, put it in terms of your coordinates, and that's challenging sometimes with the geometry, but hey, this is equal to mass total, L total, from negative L over 2 to positive L over 2 of x squared dx. Pause, do it, and then come back. You back? Okay. You did it? So what'd you get? You got I total for this case, and you might want to, just remind yourself that this is a special case, right? Through the center of mass, axis A, whatever. Mass total over L total. The integral of x squared dx is x cubed over 3 from the limits of integration. So that would be x cubed over 3 from negative L over 2 to L over 2. All right, great. Let me see, that's mass total, L total, and then I've got 1 over 3. And then I've got, oh boy, L cubed over 2 cubed, right? Which is, you know what that is? It's 8. Is that right? Is that good? 2 times 2? And then I got this one minus L over 2, what? Cubed. All right. Oh, all right. That's just, I'm not doing physics, right? I mean, math is part of physics, I suppose, but L total, I'm not even really thinking. I got 1/3 out here. Oh, I got an L cubed I can pull out, right? And that's 1 over 8 minus 1 over 8. What's going on here? What do you think? Something wrong? Did you catch that? You know, huh. How do we do this? Oh. See, it's a little thing. So things don't work out. Make sure you write it. That's cubed. There's a negative here and there's a negative. But sometimes people make, you get confused. You go, wait a minute. Wait, that's negative and it's cubed. So I still get the negative out there and that makes that positive. Oh, phew, we're good. All right, good. So, good for you to have little puzzles that you can solve. M total, L total, times L, well, I don't need the total anymore, that's what L means, L cubed, over 3, times that plus that, 2/8, 1/4. Ah, wait, that's looking like 1/12 M total L squared, because that's L squared. Cool. It has the right units, right? I mean, that's another way to check. I need to go back and make sure I don't skip like that step, because I could make that mistake so fast. It has units of, say, kilogram meter squared, so that's good. And so frequently our result is the total mass times like the largest length squared times some factor out here. So this has the form of some fraction, not frequency here, times ml squared. It can't be L cubed because that's not the units of rotational inertia. But it all worked itself out, didn't it? Okay, cool. So now I've got that. Let's do it again. So let's do this for another axis of rotation. Let's try the end. So I'm going to do the same guy here, right? But I'm going to choose a different axis of rotation. Okay. So 1, do this with the integral technique. Okay. So I'll do it fast, but make sure you do. I did that little example up there, little blunder. If you skip too many steps, you're going to really get messed up and tangled. It'll spend a lot of time. If you write down your steps, you'll catch your mistake real quickly. Okay. All right. So we need to do this. We got our axis and our object. What I've got over here, I need my chunk. So my chunk somewhere, it could be here, whatever. There's my chunk here. I mean, green on the other one. That's fine. Let's make it green. There's my chunk. Fine. And now I need my R. Where's R? Oh, it's from here to here, right? That's R. That's the distance from the axis to my chunk. Good. And then I need to, well, I can put that in terms of a coordinate system. So X, if I have X here, right? And let's see, what have I got here? I need to do, oh wait, shoot, I keep forgetting, what am I doing? Let me write this in my head. I'm looking for the total I of all the chunks. And so that's equal to the integral R squared dm. Oh, look, that gives me this guide, so a checklist. I showed my dm, I showed my R, now I need my limits of integration. What are they? What, from 0? So what would that be? From 0 to negative L? Would it be from L to 0? Would it be from negative L to 0? Does it matter if I'm rotating around? If I rotate it over here, so could I do from 0 to L? Now you can watch me all day. You know how to do it. Put pen to paper, check all these cases, because physically the resistance to changes in rotation around this axis shouldn't care what axis you use. So go through and do that. Now I'll get the answer fast because I'm going to let you do the grunt work. And so I'm going to use the parallel axis theorem to check my answer. But you can get the answer, you can look up the answer, whatever. But what you're training is being able to set up those integrals. So here's a nice little exercise to make sure that you know all the steps and you gain confidence. So if I do that, I say, let's see, I'm going to call this axis, axis B. And the axis through the center of mass, axis A, which I already got. So I through axis B, which is parallel to A by necessity, is equal to I through A, center mass, plus the total mass times the distance squared from A to B. All right, cool. And I know what that is. That's equal to this guy I just found, right? That was 1/12 ml squared plus. Now, pause and think intuitively. More rotational inertia around axis A or B? If you haven't, then you should feel that. Don't just get something, go grab something or feel it again. I know you've already felt it. Feel it again. Okay, so what have I got here? This is equal to plus m. Now what's the distance from A to B? I chose it at the end, so that distance from axis A to axis B is L over 2. So L over 2 squared. All right, let's just do some algebra. This is great. I don't have to think about physics anymore. Jeez, it's so hard. Okay, so IB through the end and parallel to the center of mass is 1/12 ml squared plus ml over 2 squared. So that's 1/12 plus 1/4 ml squared, and that's 1/12 plus 3/12 ml squared, and that's 4/12, and that's, don't do that, don't be too sloppy because that wouldn't be equal without that squared, and that's 1/3 ml squared, which is what you should have got by integrating it. If you can't get it by integrating, then you haven't got something tuned up with your integrating. So that works. Now the beauty is, I can do that around any axis, right? And you can too. Any axis parallel to that axis A works. So you can imagine this, maybe it's tied to a string, or who knows, it's on a platform and it's rotating. There's axis C, axis D, as far as you want, or in here, right? And so that parallel axis term works nicely, or you just set up the integral. Might just set up the integral. You could do this. Now, if you're going around that axis, that's interesting because, if I choose a chunk, I need to choose chunks that are parallel to the axis of rotation. So it would be just this little bit. If you can imagine, it'd be pretty easy to spin that thing right around like that, right? Okay. So that's interesting. If I choose to rotate around this axis, if I choose to rotate, say, around the x-axis, then here's y, and then I need to choose my chunk parallel to that axis, because here would be a chunk, here would be the distance around the axis, the r, which is now y, this would be dy, and of course you can choose any axis, this axis, this axis, this axis, whatever, but still choose your chunk parallel to your axes, and then that'll work out pretty nicely, and you can move it around and just experiment. And so, real quick, other note, then, if you take a look at this, and I'm going to go ahead and rotate there, what difference does it make if you have a very wide object that's rotating around? Because I'd still take a chunk like this. It would still have a distance r equal to x, and it would still have a length dx, and it would still have a mass dm, and I would still integrate, say in this case, here from, say, 0 to L. And so just realize these things, and you can take any curveball that some devious professor might throw at you on an exam. Let's take a look at just a couple more little bits, and hopefully that gives you enough to do it yourself. Set it up yourself, walk through.